Jai Hind. I am Professor Devendra Singh, HOD Mechanical Engineering at AKGEC Engineering College. I am taking the course on machine design. In last lecture, we have discussed the definition of engineering design, mechanical engineering design, and machine design. Then we have also discussed the system design cycle. Then we have discussed the engineering design procedure, where the complete procedure of the design start from the very beginning, the recognition of need, and ends with the retirement of the project. Further in this lecture, we will discuss few definitions related to machine design. The very first definition related to machine design is the empirical design. Empirical design is the design based on the previous experience of the designer, and precisely we can define the design based on previous experience and existing practices is known as empirical design. In empirical design, various dimensions are set out as a proportion of certain main dimension. In this design, we decide or determine, or we recommend the dimension of various components of a system on the basis of the dimensions of a critical element of that system or that assembly. For example, this is protective type flange coupling. Here, this is the rim. Here, this is the rim. And this will cover the portion of the bolt projected outside the rigid flanges, which are connected to driving to shaft driving and driven shafts, and this is a key. Right. So the dimension of the of this thickness, the dimension of the rigid flange coupling, the hub diameter, this hub diameter, DH. It will be decided, or this hub length. Then inside the recess portion, we define on the basis of the shaft diameter. Shaft is the critical element of in this assembly. So this is empirical design. Another example is the rigid flange coupling, plain rigid flange coupling. This is not having the rim at this portion. There is no rim. This is simple flanges put together, hold with the help of the bolt, and it will connect the two shaft driving and driven shafts. So the dimension, the bolt circle diameter, the flange thickness, this is the thickness TF, and this is the diameter of hub. And when we fix, then we have to drill this portion to put the shaft inside, or to mount these flanges on the shaft. So the dimensions of various elements of the flange coupling is given on the basis of the shaft diameter. So this is called the empirical design of the flange coupling. This is an example I have given. The various dimensions of coupling are given as proportion of the shaft diameter. Then for rigid coupling, let the shaft diameter is equals to D. Then the empirical dimension for the parts of the coupling are. It is we will see in the next slide. This is the two views. This portion here, this portion, this is the recess. This is the recess, the gap. It will ensure the proper alignment of the driven shaft and the driving shaft. Then only you can put the bolts between the driving flange and the driven flange. If there is misalignment in the driving flange and driven flange, it may cause harm to the assembly, or it may create the failure of the system. So the D is the shaft diameter, then DH, small dh, is the hub diameter, and capital D is the bolt diameter, T1 is the protective rim diameter, D1 is the bolt diameter, and the outer rim. T is the flange thickness. This is the flange thickness. LH is the length of the hub. So all these dimensions we can recommend on the basis of shaft diameter. That's why that design will be called as the empirical design. So these dimensions are, this is the hub diameter, this diameter, hub diameter is this diameter. This is 2 times of the shaft diameter. This is 2 times of the shaft diameter. Directly you can recommend this is 2 times of the shaft diameter. And the material normally flange is, we recommend the cast iron here. It is essential to mention. Then the recess diameter, this diameter here. This diameter is the recess diameter, dr. This is 1.5 to 1.75 times of d. In this case, one projection, this is the spigot and recess arrangement. One flange is having some projection, outward projection like this, and other one is having the corresponding, or this is the male female arrangement, so that the perfect alignment of the driving and driven shaft can be achieved. Otherwise it will create a problem in the working of the system. Then the bolt circle diameter, where you put the bolts. This is the bolt circle. This dotted portion, this is called the bolt circle here. This diameter is d. It is 3 times of the shaft diameter. And then the outside flange diameter, this is outside flange diameter. Here if you say this is outside diameter, df, flange diameter I should say. So this is d naught, here it is written as d naught. So this is d naught, right? So d naught is 4 times of the d. Now the flange thickness, this t thickness, or here this is also t thickness, and the protective rim here, outside projection. So this dimension is also given in terms of the shaft diameter, that is 0.5 times of d. This is now the thickness of the rim. Thickness, this is T1. This is 0.25 times of d. So all components or all dimensions of the flange coupling with respect to or in proportion of the shaft here has been mentioned, and it is based on our previous experience. If material we are using the cast iron, then these dimensions will be successful for a given diameter of the shaft. This is called the empirical design. And similarly, another example, this is unprotected rigid flange coupling. Here protected rim is not there, so you can have the same dimension, hub diameter 2 times of the shaft diameter, recess diameter 1.5 times to 1.75 times of shaft diameter, bolt circle diameter 3 times of diameter of the shaft. Outside flange coupling is 4 times of the diameter of shaft. Flange thickness is 0.5 times of the shaft diameter. There is no protective rim, that's why protective rim thickness and protective rim dimensions are not mentioned here. Then rational design. Rational design, we define those designs which are having some mathematical support by using the principles of the mechanics and solid mechanics or applied mathematics. That is called the rational design. So we may precisely define, we here in rational design we use the various formulae, we perform the mathematical analysis, and we take a decision to finalize the dimension. So this is called the rational design. It is having some mathematical support. So for rational design, if we want to precisely define it, it can be defined as it is purely mathematical design based on principles of mechanics and applied mathematics, etc. In this design, mechanics of solid is used to decide the dimension of the product. The example we can take in the next slide, combined and rational design. Here we perform the rational design. We design the dimension on the basis of the concepts of the solid mechanics, mathematics and engineering, mechanics and scientific principles we apply, and we also recommend the dimension on the basis of the empirical design, and we always recommend the dimensions whichever is larger. Whether the rational design dimensions are more, then we will consider that for that design. If empirical dimensions are more, we will take the empirical dimension for that design. That design is called combined and rational design. So we can define the combined and rational design as, in this, the component is designed on the basis of mechanics, but in no case the individual dimension to be less than the existing or past practice. So if the component which having some empirical dimensions and recorded earlier, then in no case we will recommend the dimension which is lesser than the empirical design. The example of the rational design, this is one example. A line shaft rotating at 200 rpm is to transmit 20 kilowatt. The shaft may be assumed to be made of mild steel with an allowable shear stress of 42 megapascal. Allowable stresses we will take when we start this design against static load. Allowable stress is the failure stress upon the factor of safety, and factor of safety a number a designer select to provide the additional reserve strength in the design to fight against the unwanted situations. So your design will be survive and can sustain in the undesired condition also. And because the failure of any design may cause various kinds of the losses, it may cause some monetary loss, maybe life loss, may cause life loss also. So allowable shear stress. So whenever we perform the rational design, we have to, or any designer will definitely decide the allowable stresses, and it depends on the wisdom of and experience of the designer how precisely he or she decide the allowable stresses for the design purpose as far as the strength design is concerned. So determine the diameter of the shaft, neglecting the bending moment on the shaft. So there is only, we consider the torque is transmitted, only torque is acting. We have neglected in this problem as per the statement, it's dead weight, so there is no bending effect, only torque is there. So speed is given, 200 rpm. How much power is to transmit? 20 kilowatt, and the material is given allowable shear stress. Torque will cause the torsional shear stress in the material. So the desirable data is available in this example, and we can formulate this problem. We can apply the maximum shear stress theory, or we can determine the induced stress in the application, and we have the allowable shear stress. On that basis, we can formulate an equation and solve that equation. We will get the diameter of the shaft. So in the very first step for the solution, if we handle it like a numerical problem, so it is given that the speed is 200 rpm, power is to be transmitted 20 kilowatt, and we have converted it into 20 into 10 to power 3 watt, and tau is 42 megapascal tau allowable. Then very first we assume what is the diameter of the shaft, that is d, and we will have this megapascal is Newton per mm square, so we will get the diameter in millimeter in this solution. Shaft is subjected to the torsional shear stresses. So first we need to calculate the torque. This torque is P into 60 upon 2 pi n. So power is given 20 kilowatt, that is 20,000 watt, multiplied by 60 divided by 2 pi n. So if you solve it, you will get torque is 955 Newton meter, or 955 into 10 to power 3 Newton millimeter. We have to be very careful about the dimension, because this is here megapascal is Newton per mm square. So it is essential that this should be converted into Newton per mm. So this meter should be converted into Newton per mm, Newton mm. So 10 to power 3. In the next step, you will calculate the torque transmitting capacity. This is torque is equals to pi by 16 tau into d cube. In fact, pi by 16, this is pi by 16. This is solid shaft. This is pi by 16 d cube. This is nothing. This is polar section modulus multiplied by allowable stress. That will give you the maximum permissible torque you can apply or you can transmit through this shaft. So this is the torque which we need to transmit is equal to this much. So we have put it here, and this is the function of the diameter of the shaft, pi by 16 into 42 into d cube. So this is a single equation, and this is a single equation, single unknown, that is diameter of the shaft. If you solve it, you will have the diameter of the shaft. D is equals to cube root of 955 into 10 to power 3 into 16 of pi into 42. So diameter is 48.7, and then we have taken this 50 millimeter, or we can standardize this diameter from our standards. So this is the rational design of this shaft. We have the concept, we have applied the concept of solid mechanics, we have applied the knowledge of the torque, what kind of this stresses will induce due to the torque, what is the relationship between the torque and the CI stresses. So all that concept we have used, and mathematical equation we have formulated, and we have decided the diameter of the shaft. This is having some mathematical support for determining some dimension. This is called the rational design. This is shaft diameter is the rational design. Now we take another example for combined and rational design. Design of various parts of rigid flange coupling. So we will discuss only one part in this presentation, in this lecture. Design of parts of rigid flange coupling to transmit a torque of 250 Newton meter between the shaft of 25 millimeter diameter. The flange coupling is made of cast iron, and the permissible shearing stresses of cast iron is 200 megapascal. It is given here. So if you solve it, you can see this is the protective type flange coupling. So there is nothing mentioned in the problem whether this is protective or unprotected type. So if we can take any. So we have I have taken this as a protective type flange coupling. So just take a simple part, that is hub, for illustration or to understand what is combined and rational design, and apply the combined and rational design to determine the hub outside diameter. Hub outside diameter is, this is DH. We have to find out this DH. So in fact, this hub you can consider as the hollow shaft, and if this is the driving, if this is driving and this is driven, so we always wish to transmit the complete power without any loss. So this is an assumption, there is no loss in transmission of power from driving to the driven shaft. So whatever power, whatever torque is available here, that torque must be available here. So the diameter, outside diameter of the hub, you can decide by applying the concept as we have discussed earlier for the solid shaft, by considering this hub as a hollow shaft having the outside diameter as DH and the inside diameter is equal to the shaft diameter D, because it should not have very clearance between the hub and the shaft. Outside surface of the shaft and inside surface of the hub should not have very big clearance. So we are using this key to prevent the relative rotation motion. So we can assume the inside diameter of the hub is equal to the shaft diameter, and the outside diameter of the hub is DH. So we will apply the torque equation for the hollow shaft. We will compare the induced stresses with the permissible stress of the material, and we will decide the DH. And we have already discussed what is DH. DH is the 2 times of the shaft diameter, and then we compare what is our calculated value and what is our empirical value existing, or based on our existing practice or based on our previous experience, and whichever is larger we will recommend that. Or in combined and rational design, it is mentioned that in no case the dimension should be, in no case dimension should be less than the empirical dimension if the material is not different. Here I again mention the material we use for the fringe coupling is fringes for the coupling is cast iron. So according to empirical design, inner diameter is the shaft diameter, that is equal to 25 millimeter, and the outer diameter of the hub is 2 times of shaft diameter, so it should be that 25 multiplied by 2 is equals to 50 millimeter. This is our empirical, as per the empirical design, this is our hub diameter. And now based on rational design, and this component is designed on the basis of mechanics of solid, but in no case the individual dimension to be less than the existing or past practice. It is the definition of the combined and rational design. So here we will use this same and empirical design we have done. It is repetition. Here, so determine the outside diameter of the hub to successfully transfer the torque of 250 Newton meter from shaft key to hub. So this is T multiplied by pi by 16 dh ki power 4 dh to power 4 minus dhi power 4 divided by dh. This is the polar section modulus of the hollow shaft multiplied by this permissible shear stress. This will give the maximum torque which can be transmitted by a hollow shaft. So here dhi is equals to the shaft diameter. We only require to dh. And torque is given 250 Newton meter. That will be 250 into 10 to power 3 Newton millimeter. If we put this value here, all values you put, and you calculate the value of dh, you will get dh. This equation you will get, and if you solve it, then dh will come out 29.75 millimeter, whereas the empirical dimension for the hub was 50 millimeter for the same, and the rational dimension is 29.75. So as per the definition of combined and rational design, in no case the dimension should be less than the empirical design. So we will recommend the dimension equal to dimension of the hub diameter is equals 50 millimeter. So this is called the combined and rational design. If our rational dimension comes out to be 54 millimeter, for example, if it will come out, for another example if we take, then the dimension we will recommend is 54 millimeter. We will never recommend the dimension less than the empirical dimension if empirical design is available and material remains same. Then design by innovation. So design by innovation means if we are using something, if we are adding something to make the design process faster and easier, that is called the design by innovation. For example, we have our conventional design procedure for designing the shaft or various mechanical components we can design by conventional design. Nowadays we are having various softwares available, and if we apply these softwares in our design, then this is called the design by innovation. The design is faster in that case. So the innovation, design by innovation, may be subjected to the big challenges or maybe dangerous, having more danger to failure, because here in place of designers, some software has to decide what is that. So to get faster and bolder solution, various new inventions like CAD, ANSYS, etc. need to implement in the field of design. Thus this design is known as design by innovation. This is a difference between invention right? So this is design by innovation. The same design you are using some aid to make your design faster and better. That is designed by innovation. Such designs are having greater risks, definitely. Then next is the new design. New design are those designs which start from the sketch idea. The designs which have not been tried earlier till and you are trying to get some solution for the problem. That is called the new design, or it may be called the inventive design. It may be called the inventive design or a creative design. So you can define the new design. The designs are created from the sketch idea through the application of scientific laws, technical ability, and creative thinking, known as new design. The new design may also termed as inventive or creative design. So we must able to understand what is difference between inventive design and the innovation design. In innovation, we are using something to make something faster or more appropriate, or more or make able to fulfill the demand. In new design, you are using the new idea which has not been applied earlier to for any problem. And some examples we can take: if a problem arises that says a machine for solution and no suitable machine exists, then the designer has to create it. It is called new design. A machine was designed to separate the fertile seeds from infertile seeds having same size, but the infertile seeds are of lesser weight as compared to that of fertile seeds. So designer uses the law of gravity in machine for separating the fertile seeds. If no machine exists to work on this principle, then the design machine will be considered as new design. Otherwise, it will not be a new design. It may be a design by innovation. You are using some new concept in the existing one, or then we come to the last topic for this today session. This is adaptive design or redesign. This is the design where we just change some dimension and we try to increase the capacity of a particular design. That is adaptive design or redesign. And this design comes into the picture when the developments have been seized practically, and there is no scope for further. Only we can increase the capacity of the designs. So you can define the adaptive design or redesign like: the developments have been seized practically in many fields. For example, bicycle, IC engine. So there is bicycle. You have only two wheels. If you are adding third wheel, then it is a tricycle. If you are using some engine with this, or some engine, then it is motorcycle. If we are using fourth one, then this is four wheeler. IC engine, the same slider crank mechanism, then cylinder piston arrangement, then fuel is there, ignition is there, and then slider crank mechanism will work. So this is the basic principle IC engine. What we can do in that, what we can add anything, what we can do something new with this. So we see this is practically seized, and now we can add the capacity, we can increase the capacity of the IC engine to increase the speed, to increase the load carrying capacity, etc., by adjusting the various dimensions of the various components of the engine. That is called the adaptive design or redesign. So there is hardly anything left for the designer to do except make minor modification in the dimension of the product. That is called the adaptive design or the redesign. This work is concerned with the adaptation of existing design. The final outcome does not differ much from initial product. Thus, much of work consists of redesign. If you want to increase the capacity of a or you want to apply the pressure using the same hydraulic cylinder, what will you do? Either you will increase the, if you want to get the more force from a hydraulic piston, then what will you get? The piston diameter should be more. Having the same pressure, you will get the more force, or you will increase the pressure to get the more force on the piston. So this is the adaptive or design or redesign. So this is from my side for today. And if you have any query, any question regarding this, you can contact me as per the details given in the video. Thank you very much.